All right. Hello and welcome, everyone. It's a pleasure to start today morning with Dugan Hammock. Dugan has recently joined the Wolfram Institute as a research coordinator. Dugan is originally a mathematician, more in particular a geometer. He has studied at the University of Texas in Austin and also at the University of Massachusetts, Amherst. And over the years, Dugan has worked on. I mean, before this, if I'm not mistaken, Dugan was working in quantum gravity research. He essentially has a passion for math and art, and you'll see from the talk, a lot of his work involves not only studying mathematical structures and geometric structures, but especially visualizing them, particularly things in four-dimensional visualizations, aperiodic tilings, and quasi-crystals. So today we are. It's a pleasure to hear Dugan speak about some recent work that he has been doing at the Wolfram Institute and with Stephen on what is called infrageometry or geometry on discrete systems, and perhaps there may be a little bit more about hypersurface visualizations and quasi-crystals. So thank you, Dugan, for coming here, and take it off.
Thank you for your kind introduction, Xerxes. All right, let me share a screen and I'll get started. Okay. This over. There we go.
Yeah, it's not yet loaded. Okay, there you go.
Okay, good. So infrageometry. So basically the research direction that Stephen would like to for me to go.
You could expand the font, Dugan. It's a bit small.
Yes, I'll expand it again. Yeah. Okay, so how to do geometry on things that are not manifolds. So as a sort of background, let me expand this again. Manifolds are modeled based on taking pieces of flat Euclidean space and looking at how they glue together as like a patchwork. And you get a manifold by gluing these things together. So the topology of a flat piece of Euclidean space is very limited, but as you take a patchwork of them, you can model things that are not Euclidean, for instance, tori and things like that. So the discussion of differential geometry is based on how these patches overlap and what mappings, what smooth mappings or continuous mappings can be made between these. For discretized manifolds, one approach is to use simplicial complexes, which again are pieces of flat Euclidean space, namely in this case very tightly constrained combinatorial structures such as simplices attached along their common boundary and their common vertices to make to piece together like Legos a more complicated structure. And here's an example of triangles being sectioned together to have a geometric shape. So for graphs, we want to look at discretized graphs, and we want to be able to do geometry on them. So we're going to make some assumptions that the points that the distribution of points along the spaces that we want to care about are going to be assumed to be uniformly distributed, and that, or at least locally uniformly distributed. And the distance between vertices is going to be measured by how many path edges are between points. For our purposes, I think it suffices to look at spaces that are at least locally uniform. That is, given a point in a neighborhood, the edge lengths are more or less constant. Although it could be the case that in different places, the local edge length is less or more in this case. So I want to be able to make functionality that is robust enough to adapt to spaces which are locally non-uniform. Okay. So for instance, if you're given a graph, is it possible to measure dimension? So to answer that question, we kind of look at spaces that we do know about and how dimension is measured there. For instance, on a one-dimensional line, the volume or the amount of material that you get as you increase in radius, the amount of material which is inside a line is equal to 2r. That is, you have a radius, you start from a center, you go out a radius, you measure how much in both directions, in all directions, really. So you take a ball of radius r and you ask how much material is there. In this case, you have a length, a volume degree of length being 2r. On a circle or on a flat space, a flat Euclidean space, the area or the amount of material you'll get if you expand out a ball of radius r is equal to pi r squared. So the squared term is indicating the dimensionality of the space that you're taking a ball within. Here we have, r raised to the first power. And in 2 dimensions, you have r raised to the second power. For a sphere in dimension 3, the volume inside of a ball of radius r is going to be a 4/3 pi r cubed. So you have some sort of constant term, and then a power of 3 amount of material inside. So for discretized spaces, let's say you have a point set, and you wanted to measure how many vertices are inside a ball of radius r. So for a line, so we can plot this basically using a graph distance function. Basically, you have points here, you go out a radius, you look at you count discretely the vertices that are within that. And you can plot how, as a function of radius, how many vertices you get. So here, the plot is a linear plot. So if you if you approximate this plot using a function, a coefficient, a function of this form of a times radius to some d power, where d is the dimension and a is some constant of proportionality. So here I can play with both the power and the coefficient of a fitting function to this plot. And if I set the power to 1 here and set the coefficient to an appropriate amount, I can model this very accurately using, a coefficient of 1018 times r to the first. And indeed, that aligns with our intuition that this is a linear space. For dimension 2, if I expand this point set out into 2 dimensions, I get a different plot of how many points are accumulated per radius. So here at radius, 0.3, let's say, I get about 50 points, right? And at radius 0.4, I get about 150, so on and so forth. So this is the curve of point accumulation versus radius. And we notice that it's no longer linear, but it is quadratic in its shape. So if we fit a curve to that, play with the coefficient and the power of this, we see that it obeys a more or less a quadratic distribution with some coefficient. And it does that, and then when the points start getting more sparse towards the corners of this particular example, the distribution falls off from that fit. So it makes sense to look at small radiuses and derive your power law from that fit. And for if we take a further expansion into 3 dimensions, we see that the curve bends more, and fitting a function to that, we have to increase the this exponent all the way to about 3, and we see that there's a nice cubic fit to this 3-dimensional point set. You know, some questions happen to arise. Let's say if it's mostly 2-dimensional, but it has some thickness to it, what happens? So here it's like expanding out into the 3-dimensional bulk up to and including a radius that is equal to the thickness of this rectangular sort of volume, that matching this part of the curve requires about a 3-dimensional fit. But as I expand radius out, it starts to require a smaller fit to it, a smaller dimension. So on large radii, it's 2 dimensions, and on small radii, it's 3 dimensions, and that comes out in the plot. So moving on, so a more programmatic way to instead of guessing and checking and trying to solve for 2 variables of coefficient and rate and exponent, you can use 2 sample points to excuse me. You take the volume at one and the volume at another, and you divide, and you take the logarithm of those 2 volumes, or in this case, the accumulated point set, and you can divide by the logarithm of the radii, and you can get the dimensionality that way. So you can solve for the coefficient using a different formula, but in any case, so that you can decide what 2 indices to approximate for. So for a linear point set, again, we see a dimension of 1, and as we increase, as we spread these points out into 2 dimensions, we see a best fit of dimension 2, and in 3 dimensions, we see a best fit of dimension roughly approximating 3. Now, a separate question would be to look at curvature, and I haven't gotten to that calculation yet, but I believe if you look at the volume of a ball and compare it with its surface area, that that should give you some indication. Now, separately from that discussion, is the notion of trying to do Euclidean geometry or extend the notions of Euclidean geometry to graph. So I'm going to start out with a discretization of a plane, sort of random point set there. Okay, so to make a sphere or a ball, this is a purely graph theoretic construction. So you start with a center point and you go out a certain number of steps outward. So you want to so this is a ball of radius 5. So it's taking steps outward 5 units and then accumulating all the points that are graph distance 5 away from the center. To make a line segment, again, very straightforward. This is just taking the shortest path between 2 points and drawing and accumulating all the vertices that are along that path. And so graph distance is measured by how many edges are there in that path. And we're going to treat these as straight lines. Now, one of the postulates in Euclidean geometry is that you're able to extend a straight line along a direction. So what does it mean in that case to start from point A, go to point B, and then keep going? On a pencil and compass straight edge sort of construction, you would just put these points down and have a ruler and just keep going further along the plane in the direction of that ruler. But in a graph, we don't have that luxury of having those tools. So the idea is, okay, I have point A and I go to point B using a graph theoretic straight line. And I want to extend that, let's say, a certain number of steps. So let's say I wanted to extend that 1, 2, 3, 4, 5, 6, 7 steps from that previous point. Okay, so I go from point A, go to point B. From point B, I want to go out 7 steps in the same direction. So one way to achieve this goal is to measure all the distances of all these points relative to the first point A and pick the one that's furthest away. So that is that if I measure the graph distance between this vertex and this vertex versus this vertex and that vertex, this vertex is further away from point A than any other point. And so this achieves a pretty good result of extending the line from A to B in the direction of this ray out a certain number of steps. The caveat here is so long as there's enough material in the graph to make the extension. That is to say, we're given a finite graph, or we're given some sort of graph. We don't have an infinite plane that we can just keep going in. Our space is limited to the points that we're given. Okay. Another postulate from Euclid is we want to be able to take a line in the graph, take a separate point, and then find some sort of perpendicular path dropped from this point onto here. It's a pretty straightforward construction to say, okay, the point that is dropped perpendicularly from point C is going to be the point on this line which is closest to point C. And we can see that, at least in this example, the drop perpendicular line segment going to point D is it does make right angles, at least in this example. So it's further work to see how this extends to more exotic graphs that aren't derived from the discretizations of flat Euclidean space. Now there's the notion of, okay, how do you measure angles in a graph theoretic way? Well, if we have straight lines being made and perpendiculars being dropped, so if I have a point A and point B and point C, one thing to do is to drop a perpendicular from C to line segment AB, and we get like ostensibly a right triangle from a drop perpendicular point D, and this is a right angle. So with a right angle, we can take measurements of the length along the sides of this thing and measure the angle at B. So here, perpendicular is dropped, measurements are taken. You take the arctangent of this over that, of the opposite over hypotenuse, or opposite over adjacent, and do basic trigonometry on this graph theoretic structure. And as a dynamic manipulation, we can see it's pretty accurate, at least in this case, that angle ABC here is about 45 degrees. And if I, let's see, if I put, oops. If I put point B roughly under point C, then that angle increases. Okay. And if I move C down towards A, the angle decreases to 0. Trying to get a good 90-degree result here. 75 degrees. Anyway, you get the idea. Okay. So that is where I'm at with investigations towards this. So, one of the things I need to do next is to take very exotic hypergraphs or cones or Sierpinskis and look at dimensionality there, look at what angles mean, see if you can do the same sort of constructions of extending line segments, do geometry on spaces that aren't Euclidean. Okay. Now I'm going to switch modes here and talk about aperiodic tilings and how to construct them. Okay. So a separate topic. All right. Aperiodic tilings are tilings which lack translational symmetry. You may be, I'm assuming a lot of you, or I'm hoping a lot of you are all familiar with the Penrose tiling, which is a non-periodic tiling discovered in the 70s by Sir Roger Penrose. And he was looking at trying to find a minimal set of tiles that would tile the plane without any gaps, but not tile the plane in any sort of periodic way, where you have a certain repeated section that's translationally and whose translations tile the plane. So this is there's no like a wallpaper. There's no repetition translationally. Although there is a repetition, a radial symmetry about the center of the order 5. That is, you can take this whole thing, rotate it a fifth, and it'll line up with itself. In this case, although there are aperiodic tilings which even lack rotational symmetry. Okay, so I'm going to go over a method called De Bruyn's method for constructing these. Okay, so this is a method that is purely done in the two-dimensional plane. We start with grids. So a grid is a set of equally spaced parallel lines characterized by a grid vector. In this case, a vertical line of unit length. And you have a set of parallel lines which are perpendicular to this vertical vector. So the horizontal lines are here, and you have horizontal lines equally spaced. This grid extend, these red lines extend further in the plane, but I'm only showing 7 of them. But in any case, you can label the interstitial regions between grid lines, or at least count them. So this would be the first one. This would be the second one. This would be the 0, -1, -2, etc. And for each of those integer counts, you can make a correspondence between you can count vectors. Basically, you can take that vector and start from the origin and place a vertex with that count of vectors, such that basically if I take a sample point within interstitial region number 2, I have a corresponding point on the plane that is 2 vectors in this direction. And this interstitial region corresponds to the origin. This whole interstitial region corresponds to this vector. So there's a correspondence between regions between grid lines and a set of discrete vertices in the plane. Now there are 2 different grids, horizontal and one at a particular angle, just some random angle that I chose. Again, the interstitial regions between grid lines correspond to, I'm in slab 0 of the first grid, and I'm in slab 0. Sorry, I call these interstitial regions slabs. Okay, so if I move across this this grid line, I've moved into the next gray region, and if I move again across this the second horizontal line, then I'm increasing the count of vertical vectors that I'm adding to this point's position. If I go over here, okay, if I start at the origin again and cross a red line with the sample point, then the corresponding vertex in the plane has moved. So moving across red lines will move you along the red vector, and moving across gray lines will move along the gray vector. When I add, two, let's see, so this is two vectors in the first direction and one vector in the second direction. Boom, boom, and then over. So in this case, all the interstitial regions correspond to a particular vertex, and these vertices form a discrete set in the plane. This is an example where I have 3 grids, and the vertices jump around a lot, but in each case, there's a correspondence between the open regions in the plane and the vertex that I get when I trace out 0 vertices, 0 vectors in the first direction, 2 in the second, and then 1 in the third, let's say. Or in this case, it's 2 here, 1 in the second direction, and then -2 in the third, as the case may be. I guess this one's pointing down, so negative of those vectors points up. Okay. So this is setting up a sort of, you have these grids, you have these grid lines, you have the interstitial open regions of the plane, which are between grid lines, and those correspond in a dual way to that is, each open region corresponds to a vertex. Right. Okay. Now what happens when I look at multiple sample points? If I go to an intersection of 2 grid lines and I sample the vertices around that grid line intersection, these 4 sample points correspond to these 4 vertices in the plane, and these 4 vertices in the plane make a particular rhombus. If I concentrate on, let's say I want to look at the intersection between this red one and this gray one, then these 4 regions, this region corresponds to this vertex. Okay, so this intersection of 2 grid lines corresponds to this rhombic quadrilateral. Now when I shift, whoops. It's jumping around on me. Now, if I shift the red grids, if I offset them, and I move them past those 4 sample points, it makes those corresponding vertices jump around, and the effect is that this this quadrilateral will shift laterally as the grid lines pass over it. Similarly, I can shift other grid directions and make the little quadrilateral tile translate in other directions. Okay. The Penrose tiling is made using a system of 5 grids whose grid vectors are equally spaced in the form of a pentagon. And the structure that so the rhombuses here jump around. Okay, now it's interesting that the system of grid lines is topologically equivalent via a dual construction to the Penrose tiling, but it's very difficult to see. Basically, the system of grid lines is very chaotic, and you wouldn't guess that it made something so with a high amount of structure. Okay, now this is a grid of lines. The grid lines here are modeled after a equilateral triangle, and each intersection of lines corresponds to a tile. Now in this particular example, the grid lines have a uniform structure to them. That is, they make a hexagonal grid or a triangular grid, and the dual tiling to that is when you plot out all the rhombuses that are associated with those intersections, those grid line intersections, you get this shape. You get a very regular set of a tiling. So the symmetry in the tiling reflects the symmetry that's apparent in the grids itself. Here again are only 3 grids. They have vertical, you have this slant, and you have only have 3 angles of grids here. But due to the fact that they're at a random orientations and don't have the same structure, the same regular structure, the regularity is broken up here, and consequently the regularity and the resulting tiling is also broken up. Now, when I shift the grids around, the tiles jump around discretely, and so we have a sort of a discrete path through the space of tilings. So you can kind of jostle them using the shifts in the grids. Now this is here we have the pentagrid again. So grids whose orientations are aligned to a pentagon. And so here in a close range, we have, I'm just displaying the first grid line of each grid class. And these lines, these 5 lines, intersect each other at 10 intersection points. And the inner intersection points correspond to the white rhombuses, and these outer ones correspond to these. And if I sort of move these around, then I can jostle the locations of those corresponding rhombi. And if I incorporate more lines into this, I get more intersection points. And the tiles that those intersection points make when you perform the dual operation make the Penrose tiling. And shifting the grids around will again change the location of those tiles, and the tiles will be permuted that is the same number of tiles and the same types of tiles will be jostled around, so you get different arrangements of this. Increasing the amount of grids will increase the number of tiles computed. And if I keep the offsets of the grids so if I maintain a symmetry in the offsets here, I can maintain a symmetry in the resulting tiling. If I go off range and I randomize these grid shifts, I can randomize the tiling inside. So if I move all the grids in unison, symmetric about the origin, consequently, I will have a tiling which is also symmetric about the origin, and changing the grids all at once will preserve radial symmetry in the tiling. You don't have to stop at 5 grids. Essentially, you can, so this is a 7 grid. Wait, no, it's not. I'm sorry, this is just another. Okay, here we go. You can increase the number of grids that you're dealing with. And here I have a set of 7 grids. Indeed, at the center, you see a 7-pointed star, and elsewhere, those same 7-pointed stars are represented. And the tiling can be jostled along any of these 7 by any of these 7 grid shifts, or again, moving all the grids at the same amount at the same time will preserve radial symmetry, and you can get a 1 parameter family of 7-fold periodic or quasi-crystals with 7-fold rotational symmetry, and you get a whole linear family of them. And it's very pleasing to sort of watch this dance around. Now, what's interesting is when I do this, there's a lot of dancing around on the periphery, but the inside core changes little, it doesn't change as much as the periphery does. So that's an interesting, feature of what's happening here. Increasing grid counts. We get zoom out here. Okay, so this is based on a 15 grid. And these are different variations of quasi crystal with 15-fold rotational symmetry. Here the color on the tiles is related to, it's just basically a color gradient using this based on the angle. So thinner ones are red, medium ones are blue, or the thicker ones are blue, and then you get a gradient based on that. So if I change the gradient, let's say, blue, green, yellow. So here we get thinnest ones are blue, the medium thickness rhombi are green, and the thickest rhombi, the squares, or the ones that are closest to squares, are yellow. Okay. So sometimes for very small values of the shift parameters, you can maintain a here in the center you see a regular n-gon tiled by tilings with inside of it, and I can make slight deviations in the tiling up to a certain amount. And if I go too much, that regular n-gon structure at the center gets eroded. And then it kind of goes away. So so this is a very sort of rough circle, but if I decrease this back to the origin, I get the n-gon showing up. So it's an interesting design constraint, let's say, to look at tilings which preserve that n-gon at the center. Decreasing the tile range to 0 will focus in on that n-gon and what's inside. So I started looking at what I can do with this design constraint. Okay. So looking inside, so here I'm increasing the grid count to 40, and I get a rhombic rosette within a constrained regular n-gon. And the question is, how much can I perturb these this tile set within the circle? Okay. So again, the number of grids is 40, and I have very small values for the shift parameter, the 40 shifts that I'm using, and from 0 to 0.0001, and I randomized the shift amounts, but I kept them small. And what that did is that created a aperiodic tiling where at the core of it, let me increase the grid. Decrease the plot range. Okay. Okay, so I have a chaotic tiling within the circle, and then there's a sort of a chaotic tiling outside the circle. And you can kind of see it's chaotic because these radial bands don't repeat in any sort of regular way. They're kind of zigzaggy, jagged. And that's a function of how jagged the things are inside. Now, if I decrease the variance here, whoops. this is the regular tiling, and the bands are regular. And then if I increase the randomization, then you see that the bands are randomized. Okay. Of course, we don't want it too random. So I started playing around with what can be done in this space. That if I have these shift values and I keep them relatively small, in this case, I've constrained them to 0.01 and 0.014 in magnitude and randomize their values within that band. And I get an interesting result in that the chaos of this permuted set of tiles is constrained at the center, and at the outer edge it is regular. So if I decrease this variance, I've constrained the chaotic nature of this towards the center, and if I increase the variance, I push this chaos towards the perimeter. Let's see if I can manipulate this. Yeah, pretty interesting. Now, if I vary it too much, then I start eroding away the integrity of the circle, and some tiles on the perimeter get scooted away from the circle. But if I keep the system constrained, then all the chaos gets pushed inward. All right. Now, I said before that if you kept the certain regularity in the parameters for the grid shifts, then a certain regularity, a certain radial symmetry can be preserved in the output. So here I have, again, 40 grids, and there's a sorry. So I added a repetition in the grid amount, and consequently I get a repetition in the a radial repetition in this rhombic rosette. And if I just take a couple of random values and then repeat them a number of times, then I get a radially repetitive rhombic rosette. So it's a fun exercise, and I had a lot of fun doing this. So I would do the following. I would take like a sinusoidal plot and then discretize that and get some shift values, and then make a rhombic rosette based on that. And I'll show you that. So this code is on the on my community profile. So this sinusoid that I'm using can be phased. And when you phase it, the discretization of that also gets phased as a set of all right, so you can phase the sinusoid, you can phase the grid shift values. When you do that, you get these rhombuses get jostled and permuted, and with the constraint that it's always having sevenfold rotational symmetry, and the perimeter of the perfect n-gon is maintained, and in fact the outer couple layers are always maintained, and the set of tiles within it are just permuted in place. That is to say, like, you can take a physical set of tiling, a set of tiles, the same number of them, and kind of do it paint by numbers to have a very wide variety of multiple arrangements of tilings which fill that. And so this code is available. Let's see if it still works. Oh yeah. Anyway, you can download this notebook and run it for yourself. Now, this is another animation that I made for the Penrose tiling, and that was made here, made by animating shift value number 3, and it scoots it up vertically while it jostles it, such that it makes a perfect GIF by the time you so you can make a looped GIF using the, that is to say, you can take a non-periodic tiling, jostle it in this particular way to make a periodic GIF. That's a lot of fun. Now I want to talk about a different set of I wrote a Packlet. Unfortunately, it does not run in 14.1. It runs in 14.0, and versions, the new version, I have to rewrite the Packlet to adapt to the new version. But what's going on here is I wrote a Packlet to construct convex polytopes in arbitrary dimensions. And this is successive three-dimensional slices of a four-dimensional hypershape known as the 120 cell. Okay, so this is the notebook associated with this this post. Let me zoom in here. Okay. we all know what's happening here. We have a cube and we're taking successive slices that are parallel to the bottom face, going upwards. And each slice is a square. Now, if we instead took successive slices starting from a vertex, at the bottom vertex, you get a like a triangle cutting the corner off that cube. And moving upwards, we get this moving past this first vertex, you get sort of a campered, if that's the right word, triangle, so that the edges are sort of cut in. And then the equatorial slice of a cube is a hexagon, which is interesting, I think. At least I always knew that if you took a cube and projected it and saw its shadow on the ground, what would happen is you would get a hexagon in the projection. But it's interesting to note that if you took a cube and you sliced it in half along its equator, or through the center really, in a direction perpendicular to the body diagonal of the cube, you would get two halves that stick together along a common hexagon. And then going up, you would see that hexagon let's see if I manipulate this. Let's see, do some live coding here. Change this table to manipulate. Yeah, awesome. That worked. So at the bottom, you get a triangle. It hits the corners, becomes a hexagon at the center, and then you get the reverse story on the rest of it. Okay. Same thing for the pentagon. Let's see, take the table and make it into manipulate. Oops, I didn't localize my variables, so this
It looks like Dugan dropped off. Yeah, just let's see, he may reconnect. Dugan, what happened? Are you back?
I'm back. I
Can
apologize.
you, make sure your setup is all fine?
Yeah,
Okay.
I think my roommate was messing around with the router.
Well, okay.
Okay. So yeah, you have a dodecahedron here, and at the equator and a slice that cuts parallel to the top and bottom plane, you get a dodecagon. You get a decagon, a regular tengon inside, and that's no surprise. But what was a surprise for me was to learn that if you rotate it, if you rotate the angle that you're taking a slice at, that the pentagon also has an equatorial slice of a hexagon. Which is kind of funny to think about because I wouldn't have expected that. Although I do know that there's a correspondence between the cube and the dodecahedron. In any case, so this is all fine and good. Now, the point of making this hacklet was to probe polytopes that were not that were hyperdimensional. So if you look at a hypercube, so the vertices of a hypercube are easy to define. That's just sort of tuples between 0 and 1, or -1 and +1. So if I take a cube just has it's dimension 3. So if I look at the face counts of a cube, I get for the 0-dimensional faces, that is the vertices of a cube, there are 8 of them. And so there are 8 vertices. There are 12 edges where each edge has 2 vertices on each edge. And the 2-dimensional faces of a cube, there are 6 of them. And each of those 6 faces has 4 vertices each. So that is to say 4 squares in the convex polytope of a cube. For a hypercube, you have 16 vertices, 32 one-dimensional edges, and 24 two-dimensional squares, and 8 three-dimensional things with 8 elements, 8 vertices each, which is nice to know. And if I looked at the face counts of a 5-dimensional hypercube, you get 32 vertices, 80 edges, 80 squares, 40 cubes, and 10 hypercubes as its facets, as its 4-dimensional facet. Okay, so you can take a projection of this hypercube and look at the edges and the squares and render those in a 3-dimensional plot as a projection. And this is kind of what you get. And a kind of skew projection, that is, you skew the w-axis towards like an axis in the 3 dimensions below, and then you project. You get sort of an elongated, something that you would more think about, something you would draw. You have this cube here and that cube here, then you kind of connect the vertices with edges and draw squares in between the quadrilaterals. And if I were to take progressive slices of a hypercube along a direction parallel to the first face, that is to the bottom cube, we just get a let me manipulate this too. Do some live coding. It is, as you would expect, a translation of cubes all the way through cubes that are parallel to the top and bottom faces. This is directly analogous to this progression here, where we had squares all the way through and parallel to the top and bottom square of the cube. Now, what if we wanted to do something here where we're cutting along a direction that's not parallel to one of the faces, but cuts the corner first, that kind of thing. So we can do that. So that just takes a rotation. So here the hypercube is rotated in 4th dimension before it's projected. And we're taking sort of a corner first cut. Now down by the first corner, we have a tetrahedron. And the tetrahedron slides up to where it hits some vertices, and those the corners of that tetrahedron get cut off. And towards the equator, we get sort of this octahedron in the middle. And then the other half of the story is symmetric, that it does the same thing in reverse towards the other vertex. Natural question would be to ask, what happens if you start cutting in a direction parallel to one of the edges first? So at the bottom, you have like an edge, a triangular prism. That's mostly an edge, but it fleshes out to a full triangular prism here. It goes to where it meets up with some of the first vertices it encounters, and then those edges start getting cut off. And here you have a hexagonal prism. And so that kind of mirrors that hexagon that we were seeing in the cube. initially when we were cutting perpendicular to what was it? This direction. So we're cutting along a body diagonal of the cube here. Okay. There are a lot of interesting other shapes to investigate. So here are the vertices of a 24 cell that and when you plug that in, you get this four-dimensional polytope. It has 24 vertices, 96 edges, 96 equilateral triangles, and 24 three-dimensional facets, each with 6 vertices each. Now that turns out to be 24 octahedrons. You can kind of see an octahedron in the middle. That is a square bipyramid. So this thing is sort of constructed using 24 octahedron, assembled into a kind of a spherical patchwork. And here's the same shape rendered along a kind of a skew before it's projected sort of way. And I can take this able to manipulate. So at one end, if I slice parallel to one of the octahedral facets of the 24 cell, I get an octahedron, and it clips into a cube octahedron in the center as an equatorial slice. And then out here, it evolves back into an octahedron. And if I wanted to, I could rotate it before cutting. So I'm rotating it so that it's I guess it's a vertex first, heading along a body diagonal. So it's a little tiny vertex coming in at the bottom, and that's expanding out into a cube. And in the middle, you have this sort of rhombic something made out of equal rhombuses. Some poly. There's a name for it. I forget what it is. And to get more exotic slicing behavior in between the center and the vertex here. So yeah, it's like, you know, how do you make sense of a three-dimensional figure based on a stacking of its slices? In the same way, I wanted to try to figure out a way to analyze four-dimensional shapes based on a story of a stacking of their slices. And this is a good way to do that. Now this is in 4 dimensions. There are very nice gems related to the so yeah, the platonic solids in 3 dimensions. You have the cube and the tetrahedron and the octahedron. And then you have two others, the dodecahedron and the icosahedron, which are, have a different characteristic. They're not as regular as the cubic ones. So the 600 cell in 4 dimensions is made up of taking 600 tetrahedrons and gluing them into a hypersphere and kind of closing it off, and it has 120 vertices, 720 edges, 1200 triangles, and 600 tetrahedron. And you can these are the slices of them. So let's try to let's do what we did with the other ones. Okay, so this isn't skewed in its projection, so it's just you just get the polytope that's at the slice projected to the center of the screen. And it's running slowly. But in any case, it's a larger polytope to compute. But basically, this is a story of a tetrahedron growing into whatever this shape is, and then some of the morphs into this thing. You have like these things, and along a different angle, you have along a vertex first projection, or slicing along a bidiagonal from one vertex to the next. You have an icosahedron at either end, and then it kind of campers off. You sort of have these whatever this is. So it gets very complicated and also very pleasing to look at, very beautiful. And this is sort of made out of a non-regular polytope, but still a system of regular triangles forming pentagonal sites. So you have like vertices of valence 5 and then vertices of valence 6, kind of like a soccer ball, but made out of triangles. Anyway, that's a lot of geometry. I think that concludes this talk. Thank you all for your attention.
Thank you, Dugan. Let's thank the speaker. Are there questions? We could take 1 or 2 questions and then get back to
certainly.
work.
I shouldn't do that. Yeah, other, does anyone have any questions about any of this?
If not, then let's thank Dugan again. Will you make all the material available somewhere on Discord?
Yes, I will.
Okay, great. So thanks everyone for being here. Let's have a break, catch up with your mentors, your projects, have some lunch, and we resume at 1 p.m. today. So today we'll finish off the talks early, and we'll have the rest of the day to discuss our projects. Thanks everyone.